call is now being recorded.
Good afternoon, all. Am I audible? Hello. Am I audible? Chakrapani? Am I audible? Okay, wait for 1 minute, then we will start the session. So let's start the session. This is Week 9 Microelectronics Device to Circuit session. This is a problem solving session, and I'm Arpita Biswas, a PhD scholar from IT Jodhpur in electrical engineering department. This is about me. That I did my MTech from IIIT Jabalpur in micro nanoelectronics, and I did my BTech in electronics and communication engineering from Maulana Abul Kalam Azad University of Technology. And this class schedule is every Tuesday, 7 to 9 p.m. So let's start the session. So this is question number 1. This AC schematic of an NMOS common source stage is shown in the figure below, where part of the biasing current has been omitted from simplicity. For the N-channel MOSFET M, the transconductance GM is equal to 1 milliamps per volt, and body effect and channel length modulation effect are to be neglected. The lower cutoff frequency of the circuit approximately at the first option is 8 hertz, the second option is 21 hertz, the third option is 5 hertz, and option D is 10 hertz. So take your time, there is no hurry, but at least try. And please unmute yourself and try to get the answer. Pradeep, am I audible?
Yes, madam, audible.
Oh, okay, okay. Try. Then we will discuss the question. At first, very carefully see the circuit and the values given here. The GM value 1 milliamps per volt is given, and you have to calculate the lower cutoff frequency of the circuit. Are you trying? Hello.
Yes, madam. Yes, madam.
Okay.
Last time ఒకసారి calculator ఇచ్చి.
So here given data, lambda equal to 0, and so our output 1 by lambda I output equal to infinite,
Is it
right?
175 kilohertz? 175 kilohertz? Oh, it's not there option.
No, it's not there. No? The option is
Okay.
given here. GM is 1 milliamps. There is no hurry. You try.
Okay.
And GM is given. Can you convert this circuit into a AC equivalent model? Then it will be easy to solve this type of question. So tell me how it's look like. Like in G gate side, there is an voltage source. Vi is given. Then it is connected with source. Then here GM VGS is given. This is the drain side. And then R out R0 is also parallel with this, and R0 is 10 kilo ohm. R0 not, sorry, RD. You can write RD. And here a capacitance is present, which is 1 microfarad. And here one more resistance, RL is given. RL is 10 kilo ohm. And from here we are going to calculate, and here is the V0. Now tell me how we calculate this type of, if there are this type of AC equivalent model, then how to calculate the frequency with respect to this coupling capacitor CC. Tell me how to calculate it. Do you have any idea? If
Equivalent resistance we have to find out, and 1 by 2
yes,
pi
yes.
RC. 1 by 2 pi RC. We
Okay.
are
Yes, yes.
equivalent
So
form. R
how to
equivalent
find
and C
out the
equivalent.
equivalent R? So
1,
for this
1
case,
by GM.
we have to
1.
do this voltage sources. Na, this is like the short circuit, and if or the Vi equal to 0. It's been consider Vx and Ix across coupling capacitor and disable input sources. So you have to disable this input sources, and also here you have to put a Vx and Ix, the current is coming out from this. So disable the input sources. So I'm writing here. So how the circuit look like it is short, and here it will present, but the value of gm vgs equal to 0, right? Because vi it is 0. Here vi equal to 0, so gm vgs or vi, it will be also 0 this side. And then here only present the rd, and instead of this coupling capacitor, we will like the Vx, and the current coming out from this is Ix. Okay, and this is also connected with the RL. So now can you calculate the equivalent resistor from here? Tell me what is the value of equivalent resistor here? Only see, it is zero. The value, okay, here it is gm vgs, it is zero, so it is open circuit and it is short circuit. And only here, instead of this coupling capacitor, you have to replace it by vx, and the current coming out is ix, so only this portion is remaining now. So in that case, what is the value of the r equivalent? When we are taking this circuit, in that case, this rd and rl in parallel or series. Hello, Pradeep. If the Vx is here and the current coming out from this is Ix, and only this loop is present, because here the GM VG is equal to 0, so it is open circuit, and here the voltage source which is value is 0, then in that case only this cycle is remaining. So the R equivalent here, the RD series with RL. Now tell me, what is the value of R equivalent? Hello, am I audible?
20 kilo ohm. 20 kilo ohm.
20 kilo, yes. So now we got the value of R equivalent. So how to find out the lower cutoff frequency? So the lower cutoff frequency
8 hedges, madam. Is it 8 hedges? Is it 8 hedges, madam?
My slide is not visible,
Yes,
right?
yes. Suddenly stopped.
Just wait a minute.
Okay. Now voice is okay. Only PPT pending.
now can you see the slide?
Yes, ma'am. Yes, ma'am. 8 hedges, na answer?
Yes, yes. So just so here just we have to find out the value of FL. Here we are. So here you have to find out. We just put down the value of VL equal to 1 by 2 pi RC. So 1 by 2 pi, R value is the R equivalent, which is 20 kilo ohm, and the coupling capacitor is 1 microfarad, 1 into 10 to the power minus 6. So what is the value of FL?
8 hedges.
8 hertz.
Yes, ma'am. Yes, ma'am.
Yes, okay. So the right option is first one, the 8 hertz. Okay. So this is the question number two. An amplifier is assumed to have a single pole high frequency transfer function. The rise time of its output response to a step function input is 35 nanosecond. The upper minus 3 dB frequency in megahertz for the amplifier to a sinusoidal input is approximately at the first option is 4.8, second option is 10, third option is 11.5, and the option D is 8.9. So take your time and at least try.
Madam, rise time is equal to resonant frequency by bandwidth. You are asking for the bandwidth, but I didn't find the resonant frequency value.
Have you any idea about this equation?
Yes, madam. Rise time is equal to FR by bandwidth. That I know. That I know. That I know.
Yes. From this equation, you can find out the value of the bandwidth here. Just put
Bandwidth,
down
but
all the
where
points.
is TR? FR, where
Here
is
value
it?
is given, and here you can directly take that one.
Oh, single fold frequency.
Yes.
For the from previous question, madam.
That one?
Yeah, 8 edges. Okay.
The TR value is 35 nanosecond. The bandwidth we have to find out. So it's 0.35. Then what is the value of this bandwidth? Now tell me what is the value of this bandwidth here?
Yes, yes. It's 10, madam. 10.
It is
10.
10. Yes. So question number three is for an ideal voltage amplifier circuit, what should be the value of input resistance? The first
In,
option is zero,
infinity.
infinity. Okay. The desirable characteristic of a transconductance amplifier are first option is high input resistance and high output resistance. The second option is high input resistance and low output resistance. The third option is low input resistance and high output resistance. The fourth option is low input resistance and low output resistance.
But give me 1 minute time, madam.
Okay, okay. You take your time. There's no.
Madam, both are increasing.
Yes, the high input resistance and high. Can you a little bit explain about it?
Yes, madam. We are taking current sampling and voltage mixing feedback amplifier, that is transconductance amplifier. Based on the configuration, I found out this.
Yes, so we can give the answer right. The input to the transconductance amplifier is voltage. output is current. To effectively couple voltage from the source, our input should be high. And to effectively deliver current to load, our output should be high. And how the circuit look like?
Series mixing and shunt current
Yes,
sampling by current.
yes. There is a VS and it is series. The RS and our in is series. Sorry, this is RN. Okay, and also here like GMVI, it is in shunt position. So this one is R0 and this is parallel with the RL, right?
Correct.
So this is the question number 5. An amplifier without feedback has a voltage gain of 50, input resistance of 1 kilo ohm, and the output resistance of 2.5 kilo ohm. The input resistance of the circuit shunt negative feedback amplifier using the above amplifier with a feedback factor of zero point 0.2 is. So the first option is 1 by 11 kilo ohm. The second option is 5 by 11 kilo ohm. And the third option is 12 kilo ohm. And the fourth option is 72 kilo ohm. So take your time. There's no hurry, but at least try. At first see what value given here. An amplifier without feedback has a voltage gain. So gain is given. Okay. A is given. And input resistance value is also given. RI value given 1 kilo ohm, and the feedback factor value is given. This beta is given zero point 0.2. So here we have to find out the input resistance of the current shunt negative feedback amplifier. So try.
Madam, 5 by sorry, 1 by 11 kilo ohm.
Okay, can you explain little bit
Yes,
how you are
madam. It
calculating
is
that?
a current shunt negative feedback amplifier. The input side shunter. So input resistance is divided by 1 plus A beta times. So Ri by 1 plus A beta. 1 kilo ohm by 1 plus 50 into zero point 0.2.
Yes. So our input feedback is equal to our input by 1
1
plus
plus A beta.
A beta.
Beta.
And if it is in for the outside, sorry, output side, then
Then it is R naught multiplied by 1 plus A
1
beta.
1 by A beta.
Yeah,
Yes.
it's a current sampling network, na? Current.
Yes. So the just we have to put the value 1 kilo ohm by 1 plus 50 into zero point 0.2. So the overall value will come 1 by 11 kilo ohm, kilo ohm. So the right option is the first one.
Yeah, that's only a match.
So this is the question number 6. To obtain very high input and output impedances in feedback amplifier, the mostly used is first one is the voltage series, second one is the current series, third one is the voltage shunt, and fourth one is the none of the above.
Current series, madam.
Okay. There is one more student. Uh, Please unmute yourself and try to give the answer.
Ramakant. Sir,
Current
Ramakant.
series. Current series.
Okay. Can you little bit explain?
Mixing use the high input impedance. Current mixing, it's just like series one. Shunt will give the high output impedance.
Okay, to obtain very high input in current series feedback amplifier. Yes, this
Current
is
sampling will give the high input impedance.
yes, the current
Series mixing will give the high input impedance.
yes, there is no need to write that one. So feedback amplifier very high input and impedance. So RIF equal to, in that case, RI into 1 plus is coming out like that, and ROF is also R0 into 1 plus alpha into beta. That's why the right answer is current series. So this is the question number 7. The amplifier transfer characteristic can be considerably linearized. So that is made less non-linear through the application of, first option is the negative feedback, the second option is the positive feedback, the third option is the extra power, and the fourth option is the none of the above. Okay.
Negative feedback, madam.
Okay.
Generally linearized through negative feedback amplifier. That's why negative feedback.
Yes, this is a, and also in sir lecture, I think is also mentioned. Just a minute. So the negative feedback desensitize the closed loop gain by the factor of dash. So the first option is
B band.
yes. This is the question number 9. The two capacitance CL and CM, as shown in the figure, primarily determine the dependence of the dash of the amplifier on the frequency. So see the circuit carefully and then try to give the answer. The first option is differential gain. The second option is common mode gain. The option C is the additive mode gain, and the last option is none of the above.
Madam, can you little bit zoom the question?
Just a minute, I'm trying to. Now can you see?
Yeah, fine, madam.
Okay, take your time. I'm coming back in 1 minute.
maybe additive mode gain, madam. One is load capacitance, another one is cm na. So we should go for cmr. So my option is additive mode gain, madam.
So, what is the right answer? Pradeep?
Additive mode gain, madam. Additive mode gain. I am thinking about CM and CL, both the things which are involved differential and common mode. I'm not sure, but presumed.
Actually, this is differential gain.
Okay.
You can recheck it. Okay, this is differential gain. So this is
If
question
possible,
number.
give me explanation. Okay.
You can go through the sir lecture also.
Okay.
He
Yes,
will
yes, ma'am.
explain
Yes, ma'am.
about
Fine,
this.
fine, fine.
This is the load transistor is
Okay.
given here.
Okay.
Okay, and they
Okay.
are giving the input from here, and this is
Okay.
considered as a. So the question number 10 is cascode refers to the use of a transistor connected in a common gate configuration to
A,
provide
madam.
current
Answer
buffering.
A. Answer A.
Okay.
Common source. Common source. It is direct lecture.
Can you little bit explain?
Yes, madam. Cascode means common source, and the current gate will be acting as a common gate, madam. So
Mhm.
that's why current buffering for the output is common source.
So you can draw the circuit directly here. So common gate first one is, the second one is common source. The V input given here, and this is V negative. Okay, and from here we are taking the output. So first one is the right answer. So this is the question number 11. I think this type of question in previous class also I have solved, but there are
Yes,
only
yes.
one student is present. That's why I have taken this question again. So please try to solve this question. For the given MOS differential pair, the common mode input VCM is applied. Both MOSFETs are identical, and following are the device parameters for both MOSFET. VTH is given 0.5 volt, and mu and CUXW by L is 4 milliamps per volt square, and the channel width modulation is 0. If the minimum required voltage access the current source is given 0.4 volt, then the maximum and the minimum allowed value of the VCM are. So you have to find out the maximum VCM value and the minimum VCM value. So carefully see the circuit and please try to find out the value. There is no hurry, you can take your time, but at least try. Pradeep, are you trying?
No, ma'am. No, ma'am. No, ma'am.
Do you need any clue how to solve?
Yeah, we should go for current equations and all the things. Previous class, I have to check.
Yes. I think there is one more student now. Are you trying? Okay, wait for 2 3 minutes, then I'm going to solve this. See here, 0.4 milliamps current is going on. So how much current is flowing from this side and how much current is flowing from this side? Tell me.
Point to point to ma'am.
Yes, 0.2 milliamps, and this side also 0.2 milliamps. So can we write down here? This is ID1 and this is ID2. So from here we are starting. Okay, ID1 equal to ID2 equal to, this value is ISS. Okay, so ISS by 2 equal to 0.2 milliamps. So to operate this circuit, all the parameters, device parameters are identical, and also to this is the current mirror circuit, and this M2 and M1 is in saturation mode. So what is the value of ID? Just a minute.
Mu n Cx W by Vgs minus Vt whole square.
Just a minute. Yes, the ID value is half of V1 COX W by L into VGS minus VTH whole square. Then what is the value of VGS? Tell me. Because here ID into 2, twice of ID equal to ISS, right? So can we write down root over ISS by mu n COX W by L plus VTH. Now just put the value and tell me what is the value of VGS. The VGS value is VGS1 equal to VGS2 equal to root over 0.4 by 4 plus 0.5. So this value is coming out 0.82 volt. So here we got the value of VGS. Now we are going to find out the maximum V input voltage. So max value of VCM VD greater than as it is a just a minute. VD greater than equal to VG minus VTH. And here we can take VG is VCM, the common mode input. Okay. So just write down the equation VD equal to VDD minus ISS by 2 into RD. So just put down the value VD1 as two transistors are identical, VD2 1.5 minus 0.2 milliamps into 5 volt, 5 kilo ohm, sorry. Okay, so the value is coming out 0.5 volt. So we are getting here the VD1 or VD2 and the VGS value. Okay. So next what we have to do, the maximum value we have to find out, which is VD greater than equal to VG minus VTH. Okay. So the VCM, or can we write out less than equal to VD plus VTH? Okay. So the VCM value, VD value is 0.5, VTH is 0.5. So VCM less than or get equal to 1. So the maximum VCM value is 1. Max value is 1 volt. So how to find out the minimum VCM value? Here see, the VGS value is, we have find out 0.8 to something 82, and here also the another condition is given, the current source is 0.4 volt. Here is also 0.4 volt is applied, and here minus 1.5 volt is given. So the maximum minimum VCM value is VGS 0.82 plus 0.4 and minus 1.5 volt. Tell me what is the value of this VCM minimum? Pradeep, just
Madam, I'm calculating. Okay, okay, tell me.
VCM minimum value 0.82 plus
Yes.
0.4 minus 1.5. What is the value of VCM minimum? Here is the VCM max. Okay, and this is the VCM minimum with the value.
1 minute, madam. 1.28 minus 0.28.
0.82 plus 0.4 minus
Three.
1.5
Yes, madam. Yes,
value
madam. 1.22 minus 1.5. So minus 0.28.
minus 0.28. Okay. So this is the answer. So we are moving toward the question number 12. So here in this given circuit, all MOSFETs are identical and they are biased to operate in the saturation mode. ignoring the channel length modulation effect. So lambda equal to 0 and the output voltage V output is dash. So you have to find out the value of V output, and the condition is given that all the transistor is in saturation and they are identical. So at least try.
Madam, we have to go for equivalent circuit and GM1 into R01 parallel, R04, R03 parallel, R04. We should find out output voltage now.
Without doing the AC equivalent circuit, now you can find out. Just see it, see the circuit carefully. At least try, then I will explain.
Okay.
And there is no need to convert the AC equivalent circuit. Directly, the result will come out. At least think.
Madam, 2 volts, madam. 6 minus 4, 2 volts.
Okay. I think there are one more student. No, the answer is not 2 volt.
Okay, okay.
It's not correct. Try, but you're nearly.
Yes, yes. I'm trying.
Hmm, okay. There's no hurry. Take your time.
4.8 volts. VDD minus the drop I have, diode connected load, threshold voltage. Okay, madam. We will check it. Some
Check it again. Tell me which circuit it is. The dotted line.
Current mirror, madam. Current mirror.
Yes, this one, the current mirror circuit. Okay. So if from there the 1 milliamps current is flowing, so how much current will flow from this way?
1 milliampere only.
Yes. So if 1 milliampere current is flowing from the M2, then how much current will flow from this 4 kilo ohm resistance?
Same.
Yes, same current will flow.
4 volts.
So now you are getting any clue from there how to calculate this V output?
Yes, ma'am. 6 minus oh, 4 only only 4 volts only we will get, madam. Uh,
Here 6 is connected
minus,
with that one.
yes,
So how much voltage drop from this side?
4 volts.
4 volt. Yes. So now tell me. Okay. So write down this voltage drop 4 kilo ohm is 4 volt. Okay. Then VGS3, that one. So VGS3. Now tell me what is the value of VGS3 from there? If the voltage drop here is 4 volt and it is
2
connected
volts.
with this
2
6,
volts.
so then VGS is 2 volt. 6 minus 4 equal to 2 volt. So this is the VGS3 value. VGS3 value is 2 volt. So now tell me VGS 4 value is how much?
That is 4 volts only, madam. 6
How
and
that one
6
not
is
we
there. 6 is there and 4
connected
also
with
connect.
that, and source side the V output is connected, then the value of VGS4 is
6 volts.
6 minus
4.
no. See from there na, that
Yes,
one VGS4 is that one. G side is connected with the 6 volt and
yes.
source side is connected with the V output. Then what is the
Okay.
value of VGS4? VG minus VAs for
Oh,
transistor fourth. Now tell
yes,
me what
yes.
is the value of the VGS4? 6 minus source side
Hmm.
V output, right?
Yes, yes, yes.
Yes. So VGS4 is equal to 6 minus V output. Now all of you know that the current which is flowing from this, the equation of the current, yeah, just a minute. So and from this the M4 and M3 it is in series connection. So same current will flow from this, right?
Yes, fine, fine.
So just write down the value of ID. It is in saturation mode. It is given half of. Uh, sorry, we have to write down mu1 cox, right? Mu1 cox W by L into VGS minus VTH whole square. And also both are in series, so ID3 equal to ID4, right? So write down the equation here for ID3. What is the value of ID3? Mu1 half of mu1 cox W by L into VGS. Now VGS is VGS3, right? For ID3 minus VTH whole square. And from ID4, what is the value? Half of mu1 cox W by L into VGS 4 minus VTH whole square, right? So from this side, I'm writing here, or I can erase it. Just wait a minute. Now tell me which equation we are getting from here. Hello.
Yeah, tell me, madam. Tell me.
Yes. So ID3 is equal to ID4. So from the right left side, we are getting half of mu and COX W by L VGS3 minus VTH whole square. And the right side is half of mu and COX W by L VGS4 minus VTH whole square. So the final equation, can you tell? From here, the final equation coming out. This half of mu and COX W by L cancel out. So this side only VGS3 minus VTH whole square, and right side VGS4 minus,
Square also you can remove, madam.
yes, yes, the square also you can remove. So from this side, and also the VTH will neglect.
Okay.
So VGS3 equal to VGS.
4.
So just put down the value of VGS3. Previously we have calculated now. What is the value of VGS3?
Uh, you
I
can.
think 2.
2 volts, 2 volts.
And from this side, VGS4, what
V
is the
out
value?
minus, V out minus.
No, 6. 6 minus V out, right?
Yes, yes, yes. 6
Yes,
minus.
6 minus V out.
So 2
So now tell
volts,
me what is the
4
value
volts,
of
4 volts.
this 4 volt. Now it is clear.
Yes, yes,
Okay. Just write down this, then we will move forward the next question.
yes.
So can we move towards the next question, or I will
Yes,
stay?
ma'am. Yes,
Okay.
ma'am.
So this is the question number 13. For the given cascode current mirror circuit flowing are the device parameter of each MOSFET. Threshold voltage is given zero point 0.5, mu and COX is 387 microamps per volt square. W by L is also given, which is 10, and VA is the early volt. The VA is given is 1.8 volt, and the minimum voltage required at the output for the proper operation is the current, the circuit is dash. So we have to find out the minimum voltage required at the output for proper operation of the circuit. So we have to find out the output minimum voltage. So just wait for 2-3 minutes, then we will start to solve this. Okay, let's start to solve the question. So at first see which value of given here. So Vt value is given 0.5 volt. The W by L value is given, which is 10, and mu n COX is also given 387 microamps per volt square, and Va is given 1.8 volt. So I reference also given 100 microampere. So now see. So as it is the M3 is in saturation region, and also we can, and this is the direct connected. So the M1 and M2 is direct connected. So here if we are taking the VB, and this is the VGS4, and this is these two are these four are the identical. Okay, so and also from this side we are getting the VGS. So this VGS and VGS this side, so we can write down this. If this point is VB, so VB is equal to twice of VGS. Okay, so if M3 is in saturation region, so then VD3 greater than VGS3 minus VT. Okay, and also we have to write down the VB equal to twice of VGS GS. Okay, so VD is V output. So from this transistor V output, the V0 greater than equal to, we can write down the VB minus VT. So V output minimum greater than equal to VB minus VT. So this is equal to twice of VGS greater than or equal to twice of VGS minus VT. This is minus. So from there, this current flowing from this side is 100 microamps, and also from this side the same current will flow. So ID1, can we write down this ID1 equal to half of mu n COX W by L into VGS minus VT. As all the transistors are identical, so we can write down the VGS for all cases into 1 plus lambda into VDS 1. And also we know that lambda is equal to 1 by VA, the early voltage, which is 1 by 1.8 volt, which is equal to 0.555 volt inverse. Okay, so and also given the ID1 equal to 100. Here you can see the same current will flow. So 100 microamps. Okay, so just put down the value of this 100 microamps in this equation, and what we are getting. Just erase that. So from this side, so we can write down 100 microamps equal to half of, just put down the value 387 microamps per volt square into 10 into VGS minus VTH whole square into 1 plus, what is the value of lambda, 0.555 into VGS. Okay, so here we have just write down instead of VDS1 the VGS. Why? Because here you can see the drain and gate are shorted. That's why we can write down, instead of the VDAs, we can write down the VGS. Okay. So then just try to calculate it. So 200 by 10 into 387 is coming out VGS minus VTH whole square into 1 plus 0.555 into VGS. Then what is the value of it? 0.05168 equal to VGS square minus VGS plus 0.125 into 1 plus 0.555 into VGS. Okay, just simply simplify this. So we are getting, from here we are getting the 0.555 VGS 3, sorry, VGS to cube, then plus 0.445 into VGS whole square minus 0.8625 into VGS plus 0.1983 equal to 0. So from there you will get three value of VGS. VGS value, one of them is coming out 0.69 volt. So you can, from this equation you are getting in this three value of the VGS. One of them is coming out 0.695 volt. One of them is coming out minus 1.7847 volt, and third value of VGS is equal to 0.228 volt. So the acceptable is VGS equal to VGS is equal to 0.692 volt. 69 volt. 695. 695 volt. So this is the question number 14. So for the given circuit, assume Q1 and Q2 are perfectly matched and have the following device parameters. Channel length is 1 micrometer, channel width is 10 micrometer, VTH is given 0.7 volt, and μ1 COX is given 200 microamps per V square, and lambda equal to 0. So find out the value of the R to get 100 microamps output current. What is the lowest possible value of V output? So you just have to find out the V output minimum value. So just try this one. So how to find out this? Let us see the value given here, that one. So for both transistor match perfectly when I0 is equal to I reference, and since Q1 is diode connected transistor, it is always in saturation. And also the Q2 is also in saturation. Okay. So we can write down here VDS2 greater than equal to VGS minus VTH. So I0 equal to ID equal to half of what is the equation of the current for saturation, half of mu n COX W by L into VGS minus VTH whole square. Just put down the value. The 100 microampere equal to half of 200 into 10 by 1 into VGS minus VTH whole square. So just find out the value of VGS from this. The VGS equal to 0.3, near about 0.3 voltage. Okay. So VDS2 greater than equal to VGS minus VTH. So VDS2 can we write down V output greater than equal to VGS minus VTH. So V output minimum value is VGS minus VTH, which is 0.3 volt. So V output value is 0.3. This one, the V output value is 0.3, and then we have to find out the VGS value. So VGS equal to 0.3 plus VT, and it is almost 1 volt. Okay, so from VGS, write down VGS equal to, from this side there is 1 volt. Okay, VGS equal to VDS, so this is 1 volt and here 3 volt. So the value of R we have to find out. So I reference equal to 3 minus 1 y R equal to 100, right? I reference equal to, how much current is flowing from this side? 100 microamps. Yes, 100 microamps. So from this side we have to find out the value of R. So R equal to 2 by 100 microamps equal to 20 kilo ohm. So the value of R equal to 20 kilo ohm. Pradeep, I have to explain it again, or you will go through from the
Yeah,
YouTube.
no problem, madam. I'll go through it. No issue.
Yes, okay. So here we have just have to find out the value of R. Okay, so how much R value is there? So you can go through the question. For the given circuit, assume Q1 and Q2 are perfectly matched and they have the following device parameter, and these parameters is given here. So find out the value of R to get 100 micro ampere output current. Okay, so what is the lowest possible value of the V output? So what we have done here, just we have taken, just a minute, this I output is equal to the I reference, and then just Q1 and Q2 is the Q1 is direct connected with this Q2. So this both two transistors are in saturation. So just we have taken the equation VDS greater than equal to VGS minus VTH, and then we have calculated the minimum value of the V output, and then we have find out the minimum as we have found out the minimum value of V output, then we have find out the minimum value of this equation. We have find out the minimum value of V output, and then in the VGS value from this Q2, the VGS value we have find out from there, because VT value is given, the V output minimum value is given, so VGS value is 1. So here VGS value is 1 means here is also 1 volt present, and this is short, this drain and gate, so here also the 1 volt is present. So how much the value of the R we have to calculate. So 100 microampere current is flowing from this resistance. So how we will find out? 3 minus 1 by R equal to 100 micro. So that one, the I reference equal to 3 minus 1 by R, which is equal to 100 microamps. So just we have to find from this equation, just we have to find out the value of R, which is coming out the 20 kilo ohm. Okay, so they find out the value of R is 20 kilo ohm. So this is the last question, the question number 15. The cascade amplifier shown in the figure is operated 0.2 milliampere current for all the MOSFET, and the overload voltage V over overdrive is 0.2 volt, and early voltage VA is given, which is 2 volt. The voltage gain of the cascade amplifier is, so we have to find out the voltage gain.
From lecture, direct formula is there, madam. We have to apply that.
Yes, that one. Just see here. Just a minute. That part, there are two parts. We can divide it into the two parts. This is the first one, and this one is the second part. But what is going on? Just a minute. Just that one. So the first one is the cascade current source, and the second one is cascade amplifier stage. So ID is given here 0.2 milliamps, and V overdrive also given 0.2 volt. So overdrive voltage is equal to VGS minus VTH, right? So the value of VGS, this is for the NMOS, or we can write down the VGS minus mod of VTP. This is for the PMOS. So V overdrive mod of V overdrive is equal to mod of VGS minus VTH mod, this one, equal to 0.2. So now we can find out the transconductance value, which is twice of ID into mod of VGS minus VTH, which is equal to twice of ID into V overdrive. So just put down the value and we have to find out the GM value. Twice of ID value is 0.2 milliamps per 0.2. So it is 2 milliamps per volt. So all the transistors are identical. So we can write down GM1 equal to GM2 equal to GM3 equal to GM4 is equal to twice of milliamps per volt. So we have to find out the R's are not. So that one, the R not. Okay, this one. So all the transistor, the R0 is present. So we have to find out the R naught, which is the the formula how to calculate R naught, Pradeep.
1 by lambda ID.
1 by lambda ID. So lambda equal to, we know that 1 by early voltage. So can we write down the VA by ID? So write down the value of twice of volt by 0.2 milliamps. So here we have find out the value of R naught, which is 10 kilo ohm.
So 2 milliampere multiplied by 10 kilo ohms.
Yes. Just a minute. Just for each cases we have to find out R naught. Just a minute. So R naught is we have find out. So what is the value of AV? The gain. The gain is the GM1. From this side we are taking GM1 into the RO1 R naught in, which is parallel with the ROP. Can you tell me what is this RON and what is this ROP?
We can calculate from the ID, madam.
Yes, from here, from this side, this P
Yes.
side, with if you are taking the equivalent R naught, right? Equivalent from this M4 and M3, we will get the RO for P. P is this is the PMOS. That's why we are indicating with P. So R naught P from this side and R naught in, because this is NMOS. Okay, so we have to find out, and this is at the parallel condition. That's why the GM1 multiplied with the R naught is parallel
Parallel
with
with
R naught P. So now tell me, just a minute. Just we have to find out the R on R naught in and the value of R naught P. So R naught in is equal to, from this side we are taking R01, which is multiplied with R02 into GM2, and R naught P is equal to this M on 3, that means this M4, right? Okay, yes. This um, R naught 4 into R naught 3 into GM3. Okay, and just now you have to just calculate this value. So R naught 1 you are getting, because R01 and R02 both are same, because they are identical. Okay, so R naught 1 is 10 kilo ohm, then multiply with another 10 kilo ohm, and the value of GM we have calculated 2 milliamps per volt. So here we will get 200 kilo ohm, and from this side also we can got 200 kilo ohm. So now write down the value of AV, which is uh, previously we have, yes, GM1 twice of 2 of milliamps per volt into 100. This 200 and 200 parallel, so we can directly got the 100 kilo ohm. Okay, so the answer is 200. Mod of AV is, it is clear how we have calculated. Just from this side
Yes,
and
ma'am.
this side
Yes,
we have to find out the equivalent R naught, and then this is the parallel, so we have to just find out the mod of AV equal to GM1 into, because with respect to that one we are calculating, so GM1 into R on N inside the below side and the R naught P side. Okay, and just we have to individual, we have to find out the value of it, and all the value are same here, R03 and R04, because all the transistors are identical. So AB is equal to 200. So today up to this. Next we will meet next Tuesday 7 p.m. Okay, you can leave.
thank you, ma'am. Thank you.
Okay.